Hello, good evening, and welcome to the sixth installment of Better AI Meetup, which is where AI enthusiasts and researchers and professionals meet to share knowledge. I'm pretty glad that it's actually packed here in the spot, and I would like to welcome you on behalf of KINIT, which is a Kempeland Institute of Intelligent Technologies, Innovatrix, and Cognexa, and of course the spot which provided this place. And I think we will need more space in the future, so we'll have to think about that. The topic of today's Better AI Meetup will be generative AI, which is something that I'm sure you played a lot in the past few months with. I'm sure you tried some Midjourney or Stable Diffusion or DALL-E, or maybe posted some really silly questions to ChatGPT and then had fun with your colleagues. And today we will have two guys who actually do that, but for a living. And for science as well, but mainly for business uses. So we don't want to. I don't want to hold this for too long. So just a few organizational questions for those of you both here and watching this live over streaming. You can use Slido with hashtag Better_AI to post your questions. We won't have microphones passing around here because it's too complicated, and there's frankly too many people here, and I'm sure there will be too many questions as well. First, we will have the two presentations, which are connected because they are on the same topic. And at the end, we will try to answer any and all of the questions until we are either out of questions or out of air. So we will see. Thank you again for coming. Thanks for the sponsors to providing this. And I will now leave the floor to Lukáš, the first of our presenters. He's from Cognexa, and he's also from Technical University. And he will show you how they use generative AI to actually create annotated data sets. So Lukáš, the floor is yours.
Okay. Thank you for your introduction. So, as was mentioned, thank you for inviting me here. My name is Lukáš Vodec, and I am a researcher in the field of computer vision and deep learning. Also, as my role in Cognexa, I am a lead researcher and sort of AI architect, mostly AI architect. And I am currently still at the faculty, which is my basis for my research, and I'm still here as a lecturer for the subject neural networks. So I have it at hand, and also with my colleague Igor here. Today's talk is then for some sort of a combination of my previous experience in research for generative models at the faculty, and now at Cognexa, what we do with our business here. So when I'm talking about generative models, I mean the state of the art, I mean the neural networks. And as you have all heard in the last few months, that there have been a large go-to with the diffusion models. And they had pretty good results. But also there was some kind of fear about what will they do with the art, what will they do with others. And I would really like not to go here. I would like to go to something what is very fascinating for me, and that is that we can use AI to create data, to use AI to train on this data. So it's a kind of an AIception. And this is very interesting because for a lot of work, what we do with the neural networks and with the classical deep learning, we need annotations because we need to train the neural networks. So what are these annotations? In real life, we use labels for naming objects that we see in front of us. We use, this is a chair, this is a remote control. In text, we can put labels on the sequences of words that can represent the names of the cities, names of the songs. And these labels are actually annotations, and they are the ground truth and the expected output, what we want from the networks to predict and to give us the answers to. So this is what we are trying to give and have from the neural networks. So why do we do it? Why do we need these annotations? As I mentioned, because we are trying to train the neural networks. And right now, we have several paradigms of training the neural networks, but one the most used is the supervised learning, where we have a supervisor who is some annotator, or actually maybe even some other machine that gives labels to our input data, and then watches the neural network train on them and predict something, and then compares these outputs from the neural network as a training error to the expected data. And if this goes for a lot of iterations in one step, in one iteration, these predictions should be exactly as the supervisor predicted the expected output. So to look at what these annotations could be and how should they look like, what are their structures, we can go through the use cases of the neural networks. One of them is the classification. It's the simplest one when we want to predict the probability of the object belonging to some class. As was in the previous presentation, there was chihuahuas and muffins, and today we have two classes, and we can go like 0 and 1, chihuahua or muffin, or we can use the one-hot encoding, like 0 for the first one for chihuahua, second for muffin, and then vice versa. It's a different annotation. Or also we can have multiple classes, not just the binary classification, and we have 5 classes or even more, like when we have the Gleason score classification. Then the second one is regression, which is actually kind of easier for the training, but a bit more difficult for annotating, because we are not dealing just with discrete classes, we are dealing with the continuous scale. And it's pretty difficult to say what was the prediction, or what was the consumption of electricity, or how much should the house cost. So for the annotator, for someone who wants to set these labels, it's pretty difficult to do that. And it's even more difficult to use the regression as a more specific way, as a detection or localization. As for detection or localization, here what we want to do is we have an image. Yeah, because, I mean a computer vision, so most of the samples here will be about images. We have an image, and for detection localization, we want to find where the objects we are interested in are in our image. To do that, we need to set the bounding boxes, or the centroid. And the bounding boxes, they are given from 5 values. First 2 are coordinates, then the size of the bounding box. These are actually some kind of regression, because they can be the real numbers of values. And then we have, again, classes for the classification of the object. So we have regression and the classification in one task. And the last one that comes in mind is segmentation. And here, the annotations can be almost anything. Well, ideally, it could be binary masks, because they define where is our object located, and pretty more specifically than just the bounding box. Or they also, in the in large-scale images, like in the pathology images, they would be really big. To use the binary masks, we can use the polygonal regions. And so, what is the problem with the annotations? I mean, we can give someone like mark every dog on this image, and yeah, we actually do that. But the problem is that it takes time. It takes a lot of time. And also, when sometimes we need some specific data, what we do is that we have to give courses to someone who will annotate our data. It also takes time. And then when we want them to create big data sets for our networks, it takes even more time. And we are still waiting of when can we start our research, when can we start our business. And when we want to create even a lot of data, there is a problem when we are doing some anomaly detection, as the anomalies are very sparse in real life. So either way, they can create the data imbalance. So what do we do? What do we do? Well, what we can do is the traditional approach, and so we can increase our data. We can do some permutations. We can, do what we do with some rotations, mirroring. Yeah, but what will happen? Yeah, we will probably increase the robustness on the small distortions. But when we have 100 images of the same lion, most probably our model will overfit on that one lion, and we will not have idea that there is some Bengal tiger in the prairies. So this is not what I want to talk about. This is old way, but it's still useful. What I want to talk about is what if we used the synthetic data? That would be pretty cool, because with synthetic data, we don't need the manual labor to create them. Well, we need someone to create the data for the synthetic data creation, but then we can generate thousands or millions of images, or even other data that you need. If we have a great model, we can increase the variability of our data set, and then when we have great variability, probably we'll solve also the data imbalance. And hopefully, we will improve the performance of our expert models. And also, even the pathologists are interested if we can create the synthetic data. So, again, what are the data annotations? Well, they can be anything. And we can annotate even images if you want the classification. But in this image, is it a bug? Is it a hand? Is it a telephone? Or here in this image, is it really 0.4 or is it 0.5 already? Or here in the segmentation image of a histology images, when we want to count the classes, we don't have exact locations. There is a problem. So there is a lot of noise in the data and how to create the data and what to do with them. So to overcome these problems, we need more data, hopefully. And we need them fast. We don't want to wait for them, and we need them to look nice. So what do is we need generative models, and that's why we are here. And I'm trying to tell you something more and something nice about them. So in the last few years, I would say, there have been about 5 generative models that had state-of-the-art results. And one of them is not really used anymore. And in today's today's presentation talk, I would like to talk about the 3 of them. Which I have a personal experience with. As we can see here, these are the architectures of these 3, or actually 4 networks. And we can think about them as all of them are architecture like the encoder part and decoder part. Encoder is like the descriptor for the data. It tries to learn how these data should be represented. And then the decoder, or the generator, is trying to sample from this representation and create new data, or at least the same one as it was in the data set. And then there is diffusion model, which is kind of different, but kind of same. So I'll just go through some practical examples of what we did in our research and what we did in Cognexa. It's very nice to start with texture synthesis, because here we can have some nice looking textures and it will be like, okay, we can do even more. So the first one, the most simple one, is variational autoencoder, where we need to learn the variability of data. What is the variability of data? It's the data distribution, data, how they are represented in the latent space. The thing is, the training of a variational autoencoder is unsupervised, because the thing what it does is just trying to reconstruct the input image into the output image, and we give it some regularization term to teach it to have, for us, known distribution of the latent space. And therefore, what we can do is that we know exactly what classes are where in our latent space, because we have the distribution information about them. And therefore, when we then use our generator, or actually the decoder, we know what classes we are generating. So we know the class we want to generate, we want where is it from, and therefore we have the data, and also we have the annotations. Perfect, right? Well, actually no, because that is the problem with variational autoencoders. They have very low quality. And if you have very difficult data, what they do is that they don't have enough learning capacity to train on all of our data, and it will still be something blurry. So, as you can see, this is the results of one of our autoencoders, and we see that these are not just some permutations of the input image. They are completely new images of some tiles, of some camouflage, of some stone wall. But the quality is really low. We know about that. But the other thing is very nice, that when we have the latent space, we can iterate or traverse the latent space and create new images between our 2 samples, which is nice. So let's go further. Let's go to the, well, up until the November 2022, the state-of-the-art generative model, which was generative adversarial networks. And I think until now they're still really good, and they have still very, very great advantages. So we want them to increase the quality. We hope for them to increase the variability, and we also need them to be controllable to have the output we require from them. Just let's start with simple. What are the generative adversarial networks, so simplistically GAN? They are just two networks that are competing in a minimax game. There is a generator and the discriminator, and the generator is trying to generate fake images that would look like real images, and the discriminator will be fooled by them. Yeah, that's it. The problem is that the discriminator doesn't have any idea that the generator is generating only number 8. And it can create perfectly looking number 8s all the way, but it will have no idea that there can be even 1, 4, or 5 or anything in the training set, because it doesn't care. The only thing is to know that I want to create something that looks real. So what we need to do is add the conditional generation. We need to force it to create more samples than just one. So there's the problem with the variability. So the first thing what we can do is add the discriminator to the class, and then also we need to give the constraint, the input, I forgot to write it here, to add the input also for the generator. So it knows that when I get the noise, plus this one information about what class I have to create, it will create the desired class. And here comes the fun in it. And the research fun, actually, at least. What you can do, you need to create some kind of encoding for the generator network to need what to sample and to give you your desired results. And that's what we did. We created some very nice encoding with some, yeah, I'll just go a little further because we will see that. And even though if you create some very nice encodings, there still can be a problem because generative networks just create something nice looking, or actually what discriminator thinks that is nice looking, but sometimes you also need to change the loss function to even be more strict of what is happening here, what you want the dataset to create, the network to create. So we created a network that from 1, 2, 3, 5, 7, 17 numbers, 70 values in a vector can create new textures. And yeah, this is not very good. Because when you want someone to use your product, you don't want them to fine-tune 17 and more values in a vector. So we simplified them to just 3 in the three-dimensional space, and do 2 which even don't have to be created because you're just traversing the space and then using the random noise to create another variation of the selected class. And yeah, the quality is much higher and much better, and even useful for some other cases. So this gave us a real great confidence that okay, now we can create some new results. We can do much more. Yes, we can. We can also do the thing that we can traverse again through the latent space and generate new textures, generate new types of texture, and increase the variability of our dataset. So let's try it in some applications. First, that came to mind is like we have textures, sure, we can use it in interior or exterior design. We didn't, but someone hopefully will. And the other thing is, let's create some damages or some anomalies that we can then use for the detection, like the defects. Oh, I'm not sure if you see anything here, but there is a little scratch. Don't worry, it will get better, hopefully. So I'll try to go to the domain application of our results and our networks. If we have experience with the generative models, we know that we can use them for dataset class balancing, we can create nosy annotations, we can add the background noise, well, hopefully. And the thing is, we sometimes need the use case, and our use case was to create the damages on the car's surface. Well, there's a lot of problems with this. If you are trying to create a detector of the anomalies of the damages, you can see that there are a high variability of damages on your cars. And in the dataset, it's very difficult to obtain all of them. Then there might be problems with the But what actually here is the scratch. I mean, this white could be scratch, but yeah, actually here just the reflection. But sometimes in the reflection you have also the environment, you have sky, you have completely destroyed car. Or actually in your training data set there could be just white images from rentals, and then someone wants to use it on a golden car, which is, in our data set it was just one. And the data set had 60,000 images, even more probably. So yeah, that is a problem. And you want to create that golden car and the image on the golden cars. So what we did, we used the cycle gun, which is good for domain translation. I think Igor will tell you a bit more about that. So I'll just say that we used the original, we used one from the original paper, the defect gun. What we wanted to do just to create to normal and healthy image, add some damages, and add some segmentation mask, because we need to know where the damage is, and we wanted the encoder to find where the damage is and create it on its own, not for us to annotate it. So that was the domain shift, and it tried to find something and synthesize the defect sample. However, on the way back, it should create again the normal sample, but what we got was this. That's not really what we were looking for. So first we are finding that, okay, maybe not always we can do that. So let's try to see what our data looked like. And these were the results. There are some white dots, white scratches. It's nice, but it's not really very good looking. And even on a bigger data set with various colors of the car, it got even worse. And when you, after a few months of experiments, look at your images and see that there is something very small here, very not realistically looking, you go to depression and try to find out what went wrong. So first thing first, go to the data. And then you can see that, okay, in your data was exactly like what your network was trying to find, but not only white scratches, white dots, but also everything else. And that's the problem, because the network started not to understand what is the damage. It had no idea what to find. It tried to just change the domain, as it was supposed to. And to improve your network and improve your data, it's not simple as it seems. Igor will tell you. And so, thankfully, here came the November from the last year. Here came Visual Transformer, here came denoising diffusion probabilistic models, and he came DALL-E, and we thought, like, okay, well, let's try this. And Midjourney, yeah. So we tried. I'm not going to go technically into what is all the process here and how it works. The important thing here is just on the input, you have data, you add iteratively noise until you have only noisy image, and then the network tries to reduce the noise and get back the data. DALL-E, what does DALL-E is that from the noise, it also tries to have the input from the textual information as some text encoder, and it tries to generate the image the way that it would be very similar in lightened representation as the textual information, which is cool, because now you know that you don't need only textual encoding, you can have any encoding, and then you can have any control over this DDPM. So we did exactly that. Well, not really. What we did was a much simpler way, that we had RGB image, and we know that we have the polygonal, or actually the binary segmentation mask, and when we in the input of the DDPM, you have just image that you want to get noise to, and then just try to denoise it back. So what does it matter if it's just image, or if it's 5-dimensional, 6-dimensional, if it has 7 or 5 channels? So we just added one channel to it, and all of these images are now synthetically generated. And I think it looks much better than the previous ones. The only downside is that this one image, or actually image plus its mask, was generated after 8 seconds of generation. So after 2 hours, we got 1,000 samples. It's still better than using manual someone to paint it, but it takes a while. So I would like to go to the summary and to find out what are the problems and what are the advantages of using the generative models, and to find out that there is still the question of what we should use, when we should use what. First, when we want to create, we want to generate data, we want them to be of a high quality, we want them to be sampled very fast, and also we want to be of a large diversity to really improve our data set. Variational autoencoders do just that. They are fast and they have large diversity, but they are very low in quality. Generative adversarial networks, they are still fast, and they have large quality, but if you don't add some controllability, some restrictions, something else, the problem happens that it will go down without the high variability. And then there is the diffusion models, which have very nice quality. They have large variability because you can do anything with your latent representation, but they're slow, and I mean really slow. The 1 minute or 2 minutes of generation of those 4 images you are waiting in Crayon or DALL-E, it's not because you have slow computer, it's really that slow. It's a sequential generation. So what we want to do next is to evaluate if our synthetic data really improves the training of our expert networks. We did that, we tried that. And if we find out that yes, it does, but just go a little further for that. First thing is that we generated these images synthetically to augment our data set of cells and also the segmentation masks of the cells. Then we created the data set of equal number of images from synthetic or from real data, and then we tried to train the segmentation network and evaluate of what was the impact of the synthetic data for the real for the segmentation. And also there was a large disproportion of the data in the real data set for 1 or 2 classes. Well, we did several experiments. The 3 here are very important. First one is vanilla. We just used all of the real data for the training, and we got some results that we want to compare to. And then we used 25% or 50% of the synthetic data. And we can see that they slightly went better. I mean, this is the I-score. It's not very much, but it got better. And here we can see that some of the segments just disappeared or were more correctly classified. So we went to find out how it happened with the classes, not just the overall success. And we've seen the macrophages and neutrophils were the classes with the little information, with the little examples. And what happened? That it went almost 10% up. But with a model with the half of the data synthetic, it went down. The problem is our data weren't really that nice looking. We didn't fool the pathologist, and we definitely didn't help the network when we showed them almost only the synthetic data. So the final summary is when you want to create the synthetic data, you definitely need some control over it. When you want the annotations, you need to know what you are creating, and sometimes you just can't use only the model that is given on GitHub, but you have to change it to your own needs to create even the segmentation masks for our case. Then, after our evaluation, we found out that the synthetic data can be used for data class balancing, and also they can very much increase the variability of your data, not just some permutations and typical data science improvements that we are very used to, what we do. The biggest improvement is that the synthetic data can really spare the time of the annotators, even though we still need some data to train our networks. But this could be improved by using some semi-automatically generated data, some annotation tools that can help us increase the speed of the annotations, even though they would create the weakly annotated data because the networks can train even on them. And that would be all from me. Thank you for your attention, and well, after the presentations, I will be open for the questions. Thank you very much.
Yeah. Thank you, Lukáš. I think, as Lukáš just mentioned, if you have any questions, and I'm sure there's a lot, don't forget to post them on Slido, and we'll get to them after the next presentation, which is another guy who mostly waits for new images to load. So Igor will show you what he's spending his days on. So please welcome him. Igor, it's yours.
Thank you, Jan. So thanks everyone for being here with us today. I'm Igor, I work for Innovatrix, and I will tell you something about latent fingerprints. So as you probably all know, we have these strange patterns on our fingers, and they can be used for person identification. And this whole idea is based on the assumption that the chances for two different individuals to share the very same pattern are very, very small. And to read these fingerprints, we are typically using very specific scanner devices that will read black and white images that are like these you can see in here. And these scanners, they really they produce the best quality data that we can have. And they capture at high resolution in constant DPI, and you get very, very nice looking images. Then there is the other domain, which is called latent domain. The first one was the scanner domain. And the use of latent fingerprints is usually related to some kind of criminal investigation. So if you have like investigators coming to a crime scene and they apply some powder and take pictures with the camera, so that's how you obtain these latent fingerprints. And usually these are very difficult to get. Usually fingerprints are considered sensitive data. You will not have anyone just give you a large amount of these. And these latent fingerprints are even more rare, even more scarce. So if you want to train algorithms that are built on neural networks, you are going to need a lot of data, but this is really difficult to get data like this. And we want to improve usually matchers or extractors that need some kind of annotations, and we need to have pairs of matching scanner and latent images so that we know that there is some special feature that we are looking for. Okay, and these latent fingerprints, they have some, this domain, it has some properties like you will most surely need to do some kind of perspective correction because you cannot always guarantee that the distance between the fingerprint and the camera will always be the same. There will be variable dots per eye per inch resolution, and also the quality can be quite bad. You can have only small fragments of information in there. It can be blurry. So if you want to do a fingerprint verification, you would typically take two images, have them side by side, and analyze the features that you can find in them to decide if they are a match or not. And typically these might be low-level features like, like the minutia points, and these are basically the endings of ridges or the bifurcation of ridges. Or you can also use high-level features like cores. These would be cores and deltas. And basically you want to decide that, yeah, these minutia points, they don't match, they don't align, so there is a good chance that these persons are not the same, okay? What we want is to get a matching pairs of data, and there's not really a lot of them. There is one public data set which is very good. It is published by the NIST organization. And this data set contains just 10,000 images. And these have been acquired from only 250 individuals, 40 impressions for each person. And we really wanted to see how difficult this is. So we took StyleGAN2 generator, which is still considered a very good GAN. And we tried to make it synthesize images that look like these latent SD302 by NIST. And this is what we get. After 3 hours of training, we get something which looks like single cellular organisms. And after 1 day of training, it is barely getting to get the shape right. And after 4 days, it figured out that these latents, they have these straight lines and a certain polygon clipping mask. But other than that, the model is struggling with the rich structure. It doesn't understand really what fingerprints are. So we tried another approach, and we have used a diffusion model. This has been trained for 3 days. This is nowhere near the state-of-the-art level, but we were just curious how well it does. And these images are cherry-picked. Basically, in the 10,000 image data set, you have maybe 9,000 images that look like these. So this is the vast majority of what you can find. And images like these and these, you have only a handful of them, maybe a few tens, maybe 100. And you can see that this diffusion model is able to recognize and learn such small detail like the wave structure, the wave pattern on this, maybe it's a sheet of paper, I don't know. And there are also images of paper sheet with their markings and text written on them, and you can see that the model was actually trying to learn how to write. So this was pretty impressive, and it looks very encouraging. So let's get our task straight. We want to generate pairs of matching scanner and latent images, and we want to improve the performance of our extractor. We can think of this as image-to-image translation problem. More specifically, it is an unpaired image translation because we do not have matching pairs in our dataset, so we need to learn how to get them. And this is a topic that has been studied quite well in the literature, and there are many papers, many approaches that work well with this problem. CycleGAN is one of them. I think many of you know about it. So the CycleGAN, it basically has 2 pairs of generators and discriminators where you translate image to the other domain, then you translate it back, and you want the pixels to be basically the same. That's what it does. There is an assumption that CycleGAN will always learn a bijective projection. That means for every single image, you have only one corresponding image in the other domain. Then there is NVIDIA's MUnit. And MUnit approach has an assumption that there exists a single shared content latent space. So basically, this tells us that, in all domains, we have like an animal which has 2 ears, 2 eyes, 1 mouth, and a nose. And in one domain, it can be a cat, and in another domain, it can be a dog. So that's basically what it does. And there's also a diffusion-based approach to this, which is called UnitDDPM, and this basically has 2 Markov chains of denoising models that are conditioned one on each other. So we wanted to do some experiments with these approaches, and there are several issues that we need to think about. First is that we are limited by the resolution that our extractors were trained on, and this is 500 dots per inch. So typically when you start some generative issue or model, you would start with something small and then scale up once it works, and we cannot really do this because if we lower the resolution, then we will not see the minutia points, so it would be pointless. So we have to work in rather high resolution, 416 by 416. Second issue is that we are working mostly with black and white images, and typically you would use a saturated activation function on these generator models, and this means that we are operating on the extremes of the activation function, and these are the regions where there is very little useful gradient. And if you have multiple networks connected after each other, then these networks will not learn very well. So that's a problem. And another issue is that if you take a look at these images, then you will notice that here in the scanner domain, we have very nice images, whole fingers, all the information. But in the latent domain, there are just fragments. So this automatically tells us we can rule out the MUnit approach because there is no way that there is a common shared space. The information in here is just much lower than the information in here, okay? So this is something that we need to work out. We tried first the Unity DPM approach. Of course, we were encouraged by the diffusion success, but this turned out to be quite difficult. It was very computational and memory demanding, and it was really very, very slow to iterate, to home on some solutions. So we tried the cycle again. This was really a lot of despair, many days of despair. Well, basically, if you want to try something, then you first check out the GitHub repository and try to make the original paper work with the original data, which usually works. And then when you apply the same solution to your own data, then it of course doesn't work. And then you have to find out why. And there are basically two most popular architectures that you can use for, again, this is a UNet architecture, and one that has like these two small downsampling and upsampling blocks, and then a series of residual blocks. And this unit wasn't really working well, even though in the original paper it was the recommended one. So we tried the one with the residual blocks, and our first observation was that if you have 10, 12 maybe residual blocks, then the generator would learn to produce images which are latent, but the patterns on them are not related to the original patterns at all. And this was a problem, because the other generator, it just learned to undo the damage. So the discriminators were happy, loss functions were all great, but the images were not useful at all. So we have experimented and reduced the number of the residual blocks, and this is what we have come up with, surprisingly simple architecture with just 2 residual blocks, and this works. But the problem here is that with each residual block, the receptive field grows just very slightly, and a model like this has no way to learn the concept of the latent fingerprint, because in the scanner domain you have just a plain fingerprint, and in the latent domain you have this shape that goes around it, and it was not able to learn. So we had to help it a little bit, and we have produced an artificially generated polygon mask to guide it a little bit. This is a bit inelegant, but it works, surprisingly. And you can see that this is the image that we got, okay? We have used a deep discriminator. Typically, you will find solutions with a patch-GAN discriminator. And a patch-GAN will typically just look only at small patches. And this can work with, for example, the aerial maps problem, because even small parts of an aerial map, it just makes sense. But if you have something weird sticking out of your fingerprint that you would immediately recognize, hey, this is not right. So we need a deep discriminator that can see the whole image. And this is hard to train. So, well, after 8 days of training with 2 GPUs, we got these nice looking images, and they are nice. They are definitely latent. But they have a small issue that sometimes the generator, for example, like in this case, would just remove too much useful information. And sometimes, for example, you can notice here and here, it would make up stuff that wasn't present in the original image. And this is problematic for us, because then the original annotations are not reliable, so we don't have a perfect match, okay? So we had to come up with something better, and these are the 4 points that we wanted to improve upon. The first is of course, to preserve the significant minutia points, and to be creative in the areas where there are no significant minutia points. But there is a problem that our model has no concept of minutia points. It doesn't know what they are. So how do we do that? Well, we can resort to some nice unsupervised method, like in painting. And basically what we did was just take a giant pile of images, and we kept making big random holes in them, and then train the network to undo the damage. And this actually helps. So let's consider how would a human do this kind of task. So if I asked you, Michael, to fill in the missing image, well, you would probably recognize, yeah, that fingers, they have this oval shape. So maybe somewhere around here they would be an edge, the boundary of the fingerprint. And since we know there are cores and deltas, we can clearly see that, yeah, there is a delta. And we know that the ridges, they form certain structures. So we can guess that there would be patterns like this. And judging from the orientation of these ridges And these ridges, we can estimate that somewhere around here they would probably be a delta. And actually, if a model learns these kind of things, then this becomes much easier task. So we can see on this picture what our model did. After maybe 10 hours of training, this is actually quite good result. You can see that the shape is definitely okay, the orientation is okay, there is even something which looks like a delta. This is a very nice image, actually. So, if we take a look on our architecture, this is what it is. It is basically a sparsely connected unit. We have found out that we need to use just 2 residual blocks, otherwise it would just generate random garbage. And we also wanted the model to have the concept of the whole finger, so it needs to be a bit deep, okay? Then there are some self-attention upscaling blocks to guarantee that the image is consistent, okay? So once this is okay, then we freeze all the parameters of the left-hand side, and we call it a feature extractor. So this is a fully trained model that now has a concept of what is a fingerprint. We have also kept showing images of dogs and cats and other everyday objects, and then ask the model to give us values close to 0, so that the model also learns what is not a fingerprint. And once we had this, then we have moved on and tried to find the minutia points. You can use any library like those we have at Innovatrix or maybe any other. And if you take an image of a fingerprint and use it with the library, they will give you the positions of minutia points. But this is a black box. This is not something which will give you gradients. So we need to train our model to do the same. And again, the intuition is that not every time you see a group of pixels that looks like letter Y, that there is a minutia point. Minutia point is somewhere where the ridge ends or somewhere where there is a bifurcation of ridge. And again, ridge is not just every line you can find in an image. Ridge is something that has to be a part of a structure and inside the finger. So we need to provide all the information to the right-hand side of the model, and then it can generate a probability map. And once this is trained, again for just a few hours, then we get something like this. And now you can see that some of these red spots, they are pretty bright. So these are the significant minutia points. This is what we want to preserve. And somewhere here you can see that, yeah, there's something a little bit red, but not as bright. So these are the areas that we care less about, okay? And once we have this, then we can do our first modification to the cycle GAN. This is the basic concept, where we just do pixel L1 distance. And now we insert our models into this loop. And this means that we don't really care how the images look like. We just want the same features to be present and the same minutia points to be present. But our main issue was that the features were not preserved in the latent images. So we have to, again, do something more. But unfortunately for us, we cannot do the same trick with latent images because we don't have something that will give us the minutia points for the latents. But we know that if left unchecked, the cycle GAN will mostly learn to produce similar images. And we can add a third step. Typically you train the generators, then you train the discriminators in an alternating fashion. And now we add a third step, and we will try and learn the latent extractor on interpolated images between what the generator has learned so far since the training has started. And we do this at first by producing interpolations that are closer to the scanner domain, and as the training progresses, then we move ever more towards the more difficult images, okay? And you can see on this animation here that this is the right impulse. This is just a little nudge here and there that keeps the model in connection with also the complete cycle GAN cycle. It keeps it from removing too much useful information and also from making new stuff up. You can see that here, right where this last minutia point is. Oh, come on. Oh. You will see the animation better. So the model, it will learn to stop removing information once there is an important minutia point. Yeah, so this is where the degradation stops, and all the important minutia points are preserved. So, okay, this is nice. So this is how our modified cycle gun looks now. And we can do the same vice versa for the other direction, of course, so no surprise there. So this was the first issue. But we also wanted to get rid of the latent shape, which we had to artificially generate. So we had to use, again, the same architecture, this sparsely connected unit, which is deep enough, and this gives the model a chance to fathom the concept of the fingerprint. Okay, and the last issue was the speed, because you don't want to wait 8 times every time you change 8 days every time you change a single parameter. So we have introduced skip layer excitation blocks. These appeared in 2021, and much like in a residual block, you have these skip connections that improve the propagation of gradient in the network. The skip layer excitation blocks actually connect feature maps of different resolutions. So you can make much deeper connections. And if we add these blocks to a discriminator and the generator network, then we can see there is much shorter path from the high resolution down to the lower resolution. And this really improves the learning speed and stability of the training. Okay, so next, what we did was we added a self-regularization technique on real images, and this basically makes the discriminator learn features that are useful for reconstruction of the original image. So we use VGG, this is basically a perception loss, so we force these convolutional layers to learn features that can be later on reconstructed, and this prevents the network from training on some crazy features that you don't want. And finally, we did multi-scale discrimination, and this is our way of mitigating the problem where the latent images, they are just too small. And typically, if you want to translate a very small fragment into the scanner domain where the images are big, the discriminator, it will keep asking for bigger images. This isn't right, these are too small. And the information on this level basically tells us if the image is assembled from the right components, from the right images, right parts. Information on this level tells us if these small fragments, if these small parts are assembled the right way. And if we want to assign different weights to these levels, then we can balance this issue with the discriminator, which keeps asking for bigger images, okay? So this is what we did, and once we got everything working, then we can see this new set of images. First, you can notice that it was trained in just 2 days on a single GPU, so this makes the exploration and hyperparameter tuning much better. We can quickly iterate and find better and more models. And you can also notice that these images, well, they do what we want, because, for example, here in this image, there is an area of a fingerprint which is barely useful to us. There's no information in it. And you can see that in the corresponding latent image, there is just blur. So that's what we want. And for example, this one has a very distinctive ridge pattern, and it is also preserved in the latent. So this gives us better control over the images that we generate, and we can also generate more and different kinds. So yeah, this opened a new door for us. So that is all for me. I thank you for your patience. I think the time is just right, 10 seconds. So if you have any questions, I will be happy to answer them.
Thank you, Igor, and we'll get to your question in just a few seconds, so just stay patient, and we will sit here and continue. Thank you. Okay. Thank you that you stayed with us. Thank you guys first for your presentation. I think we should make a rule that every Better AI meetup presentation should have at least either a cat or dog's image there, because it was much interesting and much more concise. And we have quite a number of questions. And if you have some more questions, don't forget to post them on Slido. We will try to get to all of them. So we will start the first one that got the most upvotes. So if you have the time, you can also read them and upvote whatever you prefer. So you mentioned that you switched to diffusion models in November, and you got much better results, both of you. So do you think there is still some use of GANs, or are they simply superseded for basically all purposes by diffusion models in your practice?
Okay, well, I will answer this question. I would not say that they would be superseded. I would say that these techniques, they would complement each other, and they are different uses for GANs and different uses for diffusion model. Also, there are many papers or certain papers working with options how to integrate them together. Recently, there has been a lot of work in differentiable augmentations, and as it turns out, the diffusion process is one of the best means how you can do differentiable augmentations. And this paper, I think it is called Diffusion GAN. So there is a lot of effort put into joining these two methods together.
Okay, great. Lukáš, do you have some more comments maybe to this?
I think yes. As you've seen in even Igor's presentation and even mine, there's still a problem with the speed of generation of the data. The GANs, they can generate thousands of images in a few seconds, and in the diffusion models, they generated our 1,000 images in 2 hours. In 2 hours with GANs, we have about millions. So when you need a lot of data, even if you want to go for the real-time rendering and maybe create some videos, there is still a lot of space for the generative adversarial networks, and the diffusion models might have problems, at least for now. Depends what will happen in the future.
Do you think there's some space to maybe make the diffusion models faster? I mean, apart from just dropping more GPUs into the computer.
I think there is the research, at least to reduce the number of steps in the denoising regression step, but. From what I know up till now, there might be other possibilities.
Okay. On to the next questions. Did you use also synthetic validation set to see whether the model is overfitted on synthetic data?
I believe that's a question for me. Our setup was to check whether it performs better on the real data. So we created synthetic data to help the model train on them and also on the real data. But I think it would be kind of foolish to use only synthetic data to improve or to
test the validate.
Yeah, to increase the variability of our validation or test data set. Because in our case, we didn't have a great quality of the results. It was enough to let the generative network and the segmentation network to learn the new structures and to understand what are these new cells, these variations. But it wasn't enough to fool the pathologist. And also, we've seen that there are some artifacts. So if we used these data set for the validation, probably we would introduce a new bias into the data. And that would be really not something that we didn't want. So we used only real data for the validation and also for the testing.
Yeah, but probably for different use cases, this could be useful way to validate.
Yes, I think what Igor presented us, those results looked really good, and I think they could be used also for the validation.
Okay, Igor, do you have some comments to that?
Well, I would say that this is maybe a different paradigm, because usually you have a fixed data and you would find ways of better architecture and better hyperparameters so that you are tweaking the model. And you can go the other way around. You can have a fixed architecture with fixed hyperparameters, and you do experiments with the data. So you are looking for better training data, for better validation data, and you want to juggle these around to get better results.
Oh, okay. How do you ensure the synthetic data is plausible in the sense that such data could, in principle, exist in reality, and it's not just the model hallucination, which is the popular talk about the typical stable diffusion and so on?
Well, for now, as far as I know, it's very difficult to do that. I mean, let's start with something that I had experienced yesterday. There is some kind of small web service that tries to check whether the text was generated by AI. And I tested it on several inputs, and it was about, let's say, 1% of that it really worked. So it's very difficult. If the text, if the image, if the results are very, very nice, and even for the human, difficult to find that if it's synthetic or not. We even cannot annotate them just out of air. So we need something and someone to find out that okay, this was synthetic, and this was real, this was hallucination. And I mean, if we are the ones we are trying to train these networks, we can use some other types of the controlling of the network to find okay, these are the, let's say in the pathology, we need to preserve the structure of the cells. So we need to find a way of controlling the generative process to keep the structures, not to make some hallucinations.
Okay.
Well, I think there is a bit misconception about the word hallucinate, because neural networks, they don't hallucinate, they are functions. And what they do is they learn distributions. So either they can learn the distribution or they don't, but they don't hallucinate.
Okay, so yeah, don't talk about hallucinations.
That is a nice word.
Yeah, it is. It sounds much better if you have a journalist article talking about hallucinations than just randomly generating noise. Okay, how much data is actually needed to train a diffusion model? You used, and I think it referred to Lukáš, but I'm not sure. 1,500 data points, but is it possible even with less data?
I'm trying to remember the numbers, but I think what we trained our network, it was 60,000 samples. But the samples doesn't mean images, it means just the cutouts from the image, the polygons. And these polygons were also transformed. We also used the data augmentations, the old ones, traditional. So I think it was about 20 to 30,000 images at the beginning, or the annotated data, that actually was not only the small ones, they were even cutouts from the larger polygons. So that was the lowest boundary for what is necessary. But I think to get even better results, to get more robust results, to get more variation, as we've seen, there was a lot of white cars in our results, and yeah, that was the problem of the network. It learned that the large number of the training data was white. So the better you want your network to be generalized, the more data you need.
Yeah, especially with such complex things as car scratches, because they can be anywhere on any color. I like the golden car. Yeah, it was very showy. I think this one is again for you, Lukáš, where you presented, the augmented synthetic data. Does the synthetic data in the example that you've shown, where it was like 3 parts real data to 1 part synthetic data, does the synthetic data help because it actually looks good, or because it adds noise that helps to regularize?
That is an interesting thinking and idea. I must say we didn't check for this. It is possible because adding noise to data, it really regularizes the training of the network. But given the nature of the generated or the synthetic data from generative networks, they usually have some pattern, some something that we don't want to be in the data, and it's very similar in every input. So this noise was probably something that could even introduce more bias in the data that we've seen in the 50-50 model. So probably what I expect from the data from this model 1 to 3, it actually was more of the structures, not the noise.
Okay. Now we have a question. Assume we want to solve some image segmentation task from scratch. Based on your experience, is it better to invest in labeling or generation of synthetic data?
Do both.
Yeah, definitely.
Yeah. The unfortunate answer is that yes, do both, probably because you need both quality data and.
I think I would recommend start somewhere. You really need the basis. If you have nothing, you need some data. And then when you have at least something, you can start generating new data. So you can introduce new variability into the data set, and maybe you can spare some money and spare some time on annotating the next more thousands of data that you probably don't need because you have the synthetic data now.
Yeah. Okay. There you have it. A very practical answer to your problem. I think everybody's going home and doing some GAN and stable diffusion modeling. Would it make sense to use an autoregressive generator for fingerprints? Models like Party seem to work quite well on generating text, but it's expensive. So
I don't quite see how an autoregressive model would help with a fingerprint, because you usually have some sequence of data that you try to regress in the future. Not sure.
yeah, okay. So don't use it, or maybe do, and come to work for us, and we will do stuff with it. So yeah, what were your costs associated with your training? So this is mostly, I think it's mostly power and buying all the new GPUs, right?
Yeah, well, neural networks are no fun when you don't have a GPU.
Yeah.
So yes.
Yeah, as you've seen the days that it took, it was like either 1 or 2 GPUs. So you can imagine that if one GPU is, I don't know, maybe 500 watts. How much is this?
I would maybe give you a number. In StyleGAN 2 paper, at the end, they have published a number that they have consumed some 150 megawatts of energy while doing exploration. So if you want to do quality generative models, those are the numbers.
Yeah. You should buy a power plant as well, probably, yes.
Yeah, or use the solar.
Yeah,
energy.
Solar or windy. In the example of scratches on cars, isn't it easier for the network to just turn all images into grayscale and train it that way?
Yeah, in the beginning, we also tried that. It gave us some kind of scratches, but the thing is that scratches are just one type of damage that can happen. In the reality, they had about 7 or 10 damage types, and in these, even the color was very important to generate. Mm-hmm. And also, the base color of the car isn't always white. It's also sometimes black or grayish if it's plastic, if it's metal. I mean, yes, at the beginning it was kind of simpler to try, as we tried something to do if we can have any results. But to be useful for the customer, we needed to be more robust and also understand the colors. And also understand the color surrounding the scratch and the, let's say, paint peel or something, because even in the paint peel, when the damage is done, the structure isn't only visible color, but also the paint is pulling off. So you need to generate that something like this is happening, and you need to change even the structure of the car, and then you need the color.
Okay. Yep. But yeah, the person who was asking is quite right. We also do a lot of just grayscale conversion for other types of uses, but this is basically not the case. So, what type of hardware and provider would you recommend to use for training similar use case to the ones you had?
Well, I would say that if you want to experiment and you do not know what the correct result is, then having to pay for a cloud computing is rather expensive unless someone gives it to you for free. So I would recommend having your own hardware. And in our cases, we have some strong servers in Innovatrix, those with 8 GPUs and stuff like that. So yeah, that helps.
Yes, I can also add the information that I think I didn't say it, but it was written in the slides that the one generating the jet diffusion model generating the scratches and the damages, because there are not only scratches, there's paint, peel, rust, and something else. The results were good after 6 days, but we wanted to see what happens after permanently letting it train for then days later, and now it's running for 41 days. And that's a lot of electricity. And also, even if you are trying to pay for all of that on some cloud, I mean, it's much cheaper to buy your own servers.
Okay, and you're also storing all the like intermediate data?
We did, but it was unnecessary because we've seen that sometimes it improves, sometimes it doesn't improve, and we just check it after a while and then remove it.
Okay. So, yeah. So that's the solution for you, you know, buy the best GPU you can and let it run for a really long time and see what happens. Have you found any interesting ideas in vector graphics generation? Which is basically, you know, illustration and so on. Maybe 3D creation.
You want to start?
Well, there's a lot of work in this field. NVIDIA is basically pushing the frontiers on this one, and you can already find some generators that are capable of producing 3D objects, or you can also generate other kinds of stuff like dance moves and and basically anything that has a distribution. So, yeah.
As you are saying, I just remember that there is at least 2 papers, one from NVIDIA, and I'm not sure which one was the second one, and they really created the generative model. Right now, I'm not sure what was that, and they really created the possibility to generate 3D models and then use the domain shift to change it to some other objects. They also put the textures on it. And just to think about that, the vector graphics, it's actually not pixel-based like typical images. It's defined by some points in the like a point cloud, but actually in the points as a sequence. So it could be created not like in the way we presented here, like on the typical images, but in some sequential generator, some sequential network, some probably
ChatGPT.
Yeah, ChatGPT probably. Maybe that could work. Just if you are here, just someone could try it and tell us.
Yeah. Is it possible to train and fine-tune diffusion models on a single GPU? I would say, I would just say from what I heard, yes, but it would take a long time, but you can correct me.
Depends on how big your images are or how big your data is, because the main issue is really how to fit it into the memory. So if you have enough memory, yeah, sure, why not?
Actually, we were trying to run it on a single GPU, and then kind of older one to see what it does and what are the possibilities. And yeah, our batch size was, I think, 8 images, and the size of the batch was 64 times 64. We wanted to go higher to 128 and 128, and we ended at 2 images in a batch size, and then we found out that it lost the capability to learn anything. So that was the results.
Okay. We touched on this, but I mean, you both the guys are researchers in AI. So, what do you think will come after the diffusion models? We mentioned the GAN and diffusion combination. So, but will there be another revolution, just like we've seen, like in the past few months?
I honestly have no idea.
I think that even the denoising diffusion models were quite of a surprise for all of us to see that they really performed even better than everyone expected. Well, we don't have GPUs to train them or to have the best results. But yeah, for a while there will be modifications. I've seen variational autoencoder generative adversarial networks. It was about a year or 2 years ago, now we can also use the controllability for the diffusion models. Maybe, as Igor said, that diffusions with generative training, something maybe with the new model or with new module of the neural networks, like the transformer. If something else happens, maybe we will get another type of generator.
Yeah, so we can generate more dogs for social media. We still have the one more question to fingerprints. Assuming the generated fingerprints were used to improve a fingerprint comparing algorithm, how much do these generated images actually help?
Well, that's really hard to say, because typically when our R&D people do these trainings, they have really lots and lots of images. So basically, when you put some bit more generated data to this, you are fighting for the small decimal points, and that's really not like a 20% difference or so.
Yeah, just to put it into perspective, the current fingerprint algorithms are like really accurate. Like we are talking about 99.98%, something like that. So you know, if you see improvements, it's usually maybe in speed, maybe in size, but the accuracy you can't really perceive that much. How much does training the fingerprint network also with negative examples, like everyday objects, actually help?
I suppose this is related to what I was speaking about.
Yeah.
Well, basically the point is to give 0 or smaller values where there is no fingerprint, because if you don't do this, then you might get some bogus features, and then the image translation model would learn to generate something even if there is not supposed to be anything, because there is just something in there.
Yeah. So and we have a last question, and I'm not sure which one of you should be the guy to answer. Did you try to use image sequences with diffusion models?
Maybe I can start.
Yeah.
Personally, I didn't try it, but I've seen few papers and also YouTube videos where they use diffusion models to generate
Video.
Yeah, exactly the videos, and also create the short films of it.
Mm-hmm.
So it is possible. You just need to change the architecture, or as we did with the segmentation mask, you can use several frames as an input to denoise them and denoise them back, and to use this for training. Not sure how this would work, but there is also a way.
Okay. Thank you for all the answers. And maybe I wanted to ask you a question that has something to do with the future as well. What are you currently working on? I mean, what's your favorite objects of research? Because I mean, you have a lot of time probably waiting between networks to generate stuff. So I think you do a lot of thinking in between.
You want to start?
I do football.
Yeah.
Yeah, some computer vision apply to football. Yeah, that's what I do.
Yeah, it's secret.
Okay, so I'm not sure if I should be very secretive about my work in Cognexa, but let's say we have the Runology project. Mm-hmm. I'm not directly there, but I'm also consulting with how we can use the not regenerative models, but the classification or the segmentation models to find what are the angles of the limbs of the runner, mm-hmm. and then find other things. And also we've been working with doctors lately, mm-hmm. With the Esenius and in Nitra, and we were trying to generate isotropic images out of anisotropic images. It's from the MRI scans. Mm-hmm. When MRI makes 3 scans of the body, axial, sagittal, and coronal, then we try to take them together and create a synthetic image, the 3D image of them. Okay. For now, we have been using only the traditional approaches and the mathematical approaches, but now as the diffusion models became very popular and we've seen that they can help with generating the synthetic data, also we try to use them on the medical data, and there is also a possibility of super resolution, so we really like to see what they can do with these images as an enhancement.
Wow. So I mean, you're here for a Better AI meetup, so here you just heard how the AI gets better at, at helping people get healthier. So I think this is great. Thank you guys for attending and for showing us the future, basically. And thank you all for attending and for listening in. And I hope you will spend a lot of time now generating images of basically anything for your new business cases. And we'll be glad to hear about it from you here sometime in the future. For those who follow us, we will be in less than 2 months. At the end of April, we will be in Brno. So you can, if you don't want to come to Brno, you can watch us online. But if you want to come to Brno, please do, because it's a nice city. And we will be officially international by then. So that's also, again, Igor and Lukáš, thank you.
Thank you.
Thank you, Kinit, Cognexa, Innovatrix, and the Spot for providing this possibility, and all of you who are here in person, and it's really full today. And I have to say, we are again breaking the records of attendance, and I think I will be saying this next time as well. So you are invited to the backstage, and to the rest of you, thank you for watching us, and have a great time. Goodbye.